Hello 8th graders, in this video we are going to be discussing potential and kinetic energy. These are the first two ELRs in our new unit, and we're going to be coming back to these two topics again and again. This unit is of course called Energy and Machines, and so we have to start with some energy. So the basics is where we have to start. Potential and kinetic energy are a little bit hard to understand because you can't see energy necessarily. Energy is sometimes described as the power to do some work or the potential to do some work. We're going to deal with two very specific kinds of energy for the most part of our unit. So potential energy is when you have the potential to drop something. It's been lifted up and gravity could make it come back down. Kinetic energy is what happens when you let go. Kinetic energy is sometimes also called the energy of momentum. Right now, I need you to watch the little race car as it goes through its loop-de-loop on the bottom of the screen. And on your paper, I need you to pause the video and I need you to draw an arrow for where the potential energy is the greatest, where the kinetic energy is the greatest, and where the car has both potential and kinetic energy. If you're still watching, you've paused the video and drawn some arrows. Let's see if we agree. So potential energy is the greatest where you had to lift it up the highest. It was starting way up at the top of the ramp and had all the potential to fall down. Kinetic energy is the greatest where it's going the fastest. In other words, at the bottom of the hill when it's used up all of its potential. And there are many places along the way where it has both. I pointed to the middle of this hill where it's starting to roll back up and getting potential energy again, but it's still moving, so it still has some kinetic. The point here is that it's never just one or the other, or at least it's usually not just one or the other. It's got both most of the time. So here's what we're about to do. In this ELR, we need to practice calculating the energy. Literally, how much energy would this car have at any point along the racetrack? In the next ELR, we're going to talk about why knowing that amount is useful for objects. You're going to be applying this to your project at the end of the unit. Now, in physics, there are a lot of different kinds of energy. We're going to be talking specifically about gravitational energy for this video, because it's the easiest one to understand, which makes it a good starting place for 8th grade. Gravitational potential energy is the potential that an object has from lifting it up. So if you think about what it would take to lift something up, there are really three factors that are going to affect it. The mass of that object, whatever planet you're on is going to contribute its gravity, and how high up into the air you have to lift it are the three factors that are going to affect how much energy it takes to lift it. Well, those are the three things in our equation. We're going to measure potential energy in a unit called joules. That's Joules, not joules like diamonds. And then the other three are things we're familiar with. So mass is measured in kilograms, gravity is 10 on this planet, we measure it in meters per second, and our height we're going to measure in meters. And they're all just multiplied to each other. So let's take a couple of examples. Let's say in the picture to the left, the mass of this big red thing is 50 kilograms and we lifted it up 6 meters, and we want to know how much energy that took, or how much energy it has by doing that. Well, we just multiply across. 50 times 10 times 6, that was our mass times gravity times the height, and we get 3,000 joules. Well, one of the things that you're going to have to do with this ELR is be able to talk about what happens when you modify the variables. So what happens if I cut this in half, or double that, or triple this, things like that. I want you to pause this video and work out what would happen if you cut the height in half and what would happen if you cut the mass in half. Specifically, we want to know what would happen to the energy. If you're still watching this video, it means that you have tried those two. Here's what you would get. For cutting the height in half, before it was 6, I've just cut it in half to 3. Doing the math, it turns out that the energy is also cut in half. That makes it pretty nice. From here on in, anytime you say you cut the energy in half, it means you cut the height in half. Or if I were to say to you, let's lift it up just a quarter of the way, well, that would mean that it would just be a quarter of the energy. The height and the energy are correlated 1 to 1. Whatever you do to one is what you're going to do to the other. Now let's think about mass. What would happen if you mess with the mass? Well, if we cut the mass in half, I turned it to 25, it was 50, did the math, and it turns out that you also cut the energy in half there. That makes potential energy equation pretty handy. If you cut in half, or cut in quarter, or triple, or quadruple one of these variables, you do the same thing to the energy. So that'll be very useful to us in later lessons. Next, I need you to please pause this video and practice using that equation for these 3 questions on my screen. When you're ready to check your answers, start the video again. If you're still watching, you're ready to check your answers. For the potential energy of all 3 objects, the numbers are on your screen. You should pause and make sure that you've shown your work in the same way. Notice the dog stayed on the ground, so his energy was 0. When the dog jumps up a meter, his energy goes to 24. And in order to figure out how high the cup needs to be in order to have the same energy as the cat, I took the energy of the cat from the first question and I put that in for PE. So originally we found that the cat had 27. I just plugged that in for the energy, the cat's mass stayed the same, gravity stays the same, and then I solved for height. Pause this video if you need to check any of your answers. Now we need to talk about kinetic energy. That's the energy of motion. The reason why we need to go to kinetic is because potential energy can turn into kinetic. If you lift something up and drop it, gravity makes it move. On the other side, if you have something that's moving, it could roll up a hill, and that kinetic energy could turn into potential. In fact, that's exactly where we're going in the next DLR, so we need to be able to calculate it. Well, kinetic energy is also measured in joules. All energy is. And the equation is 1/2 times the mass times the velocity squared. Mass is still in kilograms, and velocity we've done before, that's meters per second. One tip here, if you are not super comfortable with order of operations, make absolutely sure that you do all of your squaring first when you're trying to solve for kinetic energy. Let's talk about some examples. So let's say that we want to do the whole halving, cutting in half, or halving, doubling, multiplying by 3, quadrupling, that whole thing again. Well, the rules are not the same here as they were for potential. Let's make sure we understand. So for kinetic energy, let's say that the mass in the picture is still 50, and this time when we cut the string right before it hit the stump, it was moving 12 meters per second. We're going to solve for kinetic. We plug in all of the numbers, make sure we do our squaring first. So I got 144 when I squared 12. Then we can multiply across, and we get 3,600 joules. Now for the mass cut in half and the velocity in half. Again, I want you to pause this video and work those out for yourself and start it again when you're ready to check. If you're still watching and you've checked these, or you've done these numbers yourself, you will notice that it indeed is not the same rule as it was for potential. Let's start with the mass cut in half. Earlier I said that it was a 50 kilogram mass. Well, let's cut that in half to 25 and do the numbers again. This time we do in fact get kinetic energy cut in half. So if you cut the mass in half, for kinetic or potential, you cut the energy in half. That one is going to be the same for both. But here's the thing, velocity is not the same. In the equation, since we're squaring velocity, it doesn't quite play by the same rules. So let's cut velocity in half and prove it to ourselves. Before it was 12, so I cut it in half to 6. I square first, then multiply through, and I get 900 joules. That's a quarter of my original energy. So when you mess with the velocity, you're making great big changes in the kinetic energy. Be very careful when you're dealing with velocity and making assumptions. I need you to please pause this video again and try these 3 practice questions in your notes. Start the video again when you're ready to check. Quick hint for the last question, you're going to need to undo a square root, or undo a square. In order to do that, you need to do a square root. Please flag me down in class if you need help with that. If you're still watching, you're ready to check your answers. Here are the answers on your screen. Please pause the video so that you can make sure that you have on your paper what I have on my screen.